Welcome to Thermo Video 3, which is a video all about entropy. So first part of class, or first part of school, we talked about enthalpy, which is the heat energy. Now we're going to talk about entropy, which is the disorder or randomness of a system. So all atoms are moving, electrons are moving, therefore there is chaos. Chaos is entropy. Its symbol is S. Why? I don't know. There are no S's in the word entropy. I guess we ran out of E's. Entropy is a state function, just like enthalpy is a state function, which I hope you remember the definition for state function. Just in case you don't, state function means it only matters how it begins and how it ends, not how it gets there. So you can use entropy as far as products minus reactants and final minus initial the same way that you do for enthalpy. So if you wanted to calculate the entropy of a reaction, you could do the sum of the entropy, standard entropy, of the products minus the sum of the standard entropies of the reactants, just like you do for enthalpies. And entropy is also listed in Appendix C. Again, we deal with the change in entropy. You cannot actually measure the entropy of a system at any given time because it's crazy how, like, all they're moving. How are you going to measure all that? So instead, we just measure the changes of entropy as a reaction takes place. The second law of thermodynamics tells us that no matter what kind of reaction it is, the overall entropy of the universe has to increase. Therefore, the universe is constantly becoming more disorderly, more chaotic. There is no way to stop this. There's no way to reverse this. You cannot make the universe more orderly. You're thinking, well, wait a minute. I sometimes clean my room. It's more orderly after I clean it. That is true. You can make a system more orderly, in which case your room would be the system, the things of your room. However, as you clean your room, you are burning calories. You are breaking the bonds of glucose and separating that molecule up. You are radiating heat out of your body as you are working out with all that heavy lifting, because I'm sure your room's a mess. And so that heat energy is exciting the molecules of the air. They're moving faster, moving more chaotically. So even as you are organizing one part of the universe, the rest of the universe is becoming less organized. Don't use that as an excuse not to clean your room. That's important too. However, just be aware that over the course of time, the universe will eventually become completely chaotic. And even things like this world will break apart into little pieces because everything has to get more chaotic. And eventually, the universe is going to get to a point where it is all one uniform temperature and one uniform distribution of matter. We won't be alive by the time that happens. We're talking gajillions of years in the future. But that's where we're heading. And that is because of the second law of thermodynamics. So again, the entropy of a system can decrease, meaning that we could have negative delta S. We're becoming more orderly or less chaotic. Or you could have a positive entropy, meaning that you are becoming more disorderly. The system is increasing in chaos. Okay, what kinds of reactions have negative entropies and what kind of reactions have positive entropies? It is possible, without looking at any actual numbers, but just looking at the reaction itself, to determine whether or not the entropy should be increasing or decreasing for this reaction. If we look at a solid versus a liquid versus a gas, you can see the molecules or atoms are very orderly as a solid, somewhat less orderly as a liquid, and very chaotic as a gas. So the entropy of a solid is less than the entropy of a liquid, which is less than the entropy of a gas. Remember, entropy means chaos, more chaos at that end, less chaos at this end. So if you have some kind of a chemical reaction where you are going from a solid to a liquid to a gas, you are going to increase your entropy. You should have a positive change of entropy there. For example, let's say you're taking ice, solid water, and you are melting it to liquid water. We're going from a solid to a liquid, and therefore our delta S will be positive for this reaction. So just by looking at the states of matter of a reaction and how they're going from the reactant side to the product side, that can tell us whether or not we're going to have a positive S or a negative S. Other possibilities include, how many gas molecules we have. If we increase the amount of gas we have, more molecules, more chaos. This is true anytime you're trying to babysit children. The more children you have, the more chaos ensues. Same way with gas molecules. So if we have any kind of a reaction where we go from one kind of, like two, let's see, if we go from 2 molecules of gas to 3 molecules of gas, let's say, I mean, this is not quite balanced, but if we go from 2 molecules of gas to 3 molecules of gas, then we have our increased our entropy. Sorry, this should be like a 2 here and some oxygen over here. Okay, we've increased from 2 to a total of 3 molecules of gas, and then our entropy is positive. You will be required on the AP exam to just look at a reaction and say whether the entropy has increased or decreased for this reaction. So you're looking at states of matter, you're looking at numbers of gas molecules. Have they increased or decreased? The third law of thermodynamics is also about entropy. It says that at 0 Kelvin, absolute 0, the entropy of something is 0, meaning all motion ceases. There is no chaos. It is perfectly crystalline, orderly. And there's a graph here that demonstrates that gas has a lot of entropy. It loses entropy as it turns to a liquid. It loses entropy again as it turns to a solid. And then if that solid goes all the way down to 0, which nobody ever has accomplished this, but theoretically if they did, the entropy would be 0. Let's talk about numbers with entropy. So we talked about entropy qualitatively. Is it increasing? Is it decreasing? But now let's talk about actually calculating the entropy. As I said on the previous board, you can do products minus reactants for entropy. So if you have a data table or your appendix C, or you're on the test and it gives you a portion of that, you can calculate entropy that way. Entropy has a unit of joules per mole Kelvin. We'll talk about the Kelvin later when we get into Gibbs, which is after entropy. But I want to highlight here the fact that it is joules. Enthalpy, you may recall, on your appendix C, is in kilojoules per mole. Entropy is in joules per mole. This is going to become important because later we're going to have an equation that uses entropy and enthalpy in the same equation. You gotta have them converted so that they're both the same. So you either have to convert this one to kilojoules or convert this one to joules. You cannot use kilojoules and joules in the same equation. We'll get to more of that when we hit Gibbs. Other things you'll notice on your appendix C is that yes, the delta H for any element is 0. We don't form elements and therefore no heat is produced in the formation of them. However, the delta S for an element is greater than 0. Not that you're forming the element, we don't put F's here with entropy. But there's always chaos. Unless you're at absolute 0, which you're not if you have this little symbol here, because that means standard state, we're at 25 degrees Celsius. But as long as you're not at absolute 0, your entropy is not 0. It's something greater than 0. These numbers are always positive. This number can be negative, endothermic versus exothermic. The change in entropy for a reaction can be positive or negative. However, the entropy of a molecule or an atom is going to be positive. All right, so let's compare some numbers for a couple of things on our appendix C. So if we look at scandium solid versus scandium gas, you'll see that scandium solid is 34.6, scandium gas 174.7. Why is this one greater than this one? Well, gases are more chaotic. All right, let's try another pair. Ammonia gas versus aqueous ammonia. 192.5 versus 111.3. Again, gases are more chaotic. Notice there was a much bigger difference between a gas and a solid than a gas and an aqueous solution, but it's still going to be greater for the gas. All right, here we have 1 mole of P4 at 280, 2 moles of P4 at 436.2. Well, they're both gases. It's because of the greater moles. So more moles equals more entropy. Graphite versus diamond. They're both carbon, they're both solids. They're both the same number of moles. Graphite is 5.69 joules per mole Kelvin. Diamond is 2.43 joules per mole Kelvin. Very little entropy. Both of these are highly ordered, highly rigid structures. What's going on here? You may remember from pre-AP chemistry that carbon can bond to itself in a variety of ways. Graphite is carbon bonded to itself. So this is a carbon atom here. Bonded to another carbon atom, bonded to another carbon atom, and so on and so forth. And there's that one. You can have the graphite of carbons bonded to carbons, and so on and so on. And then you have sheets of this. So then we have another set of carbon. These are covalent bonds. Carbon bonded to carbon, bonded to carbon, bonded to carbon. And then these are held, these sheets, are held together with intermolecular forces. Molecular forces. So the sheets themselves are very strong. However, between the sheets are very weak intermolecular forces. So this is a covalent bond. Covalent bonds being the strongest kind of bonds in the universe. But the sheets are held together by intermolecular forces, and so the graphite slides off each other. So that's what happens when you write. Your pencil is not made of lead, it's made of graphite, and you can't see the sheets, but as you write on the paper, a sheet of graphite slides off your pencil onto the paper, and that is the mark. And that can be rubbed off with an eraser. Diamond, on the other hand, is completely bonded by covalent bonds. There are no intermolecular forces involved in diamonds. Therefore, diamonds are the hardest substance in the world. Something like that. Okay? This is called a network solid. So when you look at a diamond, you are actually looking at one gigantic molecule, because every atom of carbon in the diamond is covalently bonded. And a covalent bond denotes a molecule. So it's one giant molecule held together by extremely strong covalent bonds. That's why diamond is so hard to break. And that's why it's so orderly. These atoms aren't going anywhere. So there are the various reasons for why you can have more chaos in one system versus the other. You don't even need the numbers, but they just back you up on your knowledge. Gases are more chaotic, more moles equals more chaos, and this is a very special case of a diamond being less chaotic than graphite. Okay, let's look at 4 hydrocarbons: methane, ethane, propane, and butane. Each of them contain exactly the same 2 elements. Each of them are gases. However, the entropy increases 186.3 to 229.5, and so on and so on. Why is the entropy increasing when they're all gases? There's none of this network solid thing going on. We have the same number of moles. Well, the reason for this is that entropy increases as molar mass increases. That fancy M is molar mass. Molar mass increases. It also increases as the number of atoms in the molecule increases. So here we have 5 atoms in this molecule. Here we have 8 atoms, and 11 atoms, and 14 atoms. So as the number of atoms increases, also the molar mass is increasing, and therefore there is more entropy as you go up this list. So hopefully that gives you some good grounding in how to identify reactions that are increasing in entropy or decreasing in entropy. You need to know how to do that. You need to be able to compare 2 things and discuss which one would have greater entropy and why. And you have several reasons for that. Again, changes of matter, changes of states of matter, increase of gas production, more moles of gas on the product side would be more entropy, and the special case of the graphite versus diamond, and also as your molar mass increases and your number of atoms increases, your entropy increases. Thank you.